Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. On February 1, 1922, parallel processing, or solving a million problems at once, entered into the realm of science fiction. But it was not until July 4, 1989, or 67 years later, that I discovered practical parallel processing. I discovered practical parallel processing as the vital technology that now underpins every supercomputer that is manufactured today. For 67 years, onward of 1922, parallel processing was the big and unanswered question of the field of computing. For 67 years, parallel processing was mocked and ridiculed as the beautiful theory that lacked an experimental confirmation. But on the 4th of July, 1989, parallel processing was upgraded from science fiction to supercomputer reality. That was the date that I discovered parallel processing and discovered it across a new internet that was a new global network of 64 binary thousand processors. That experimental discovery was the lockdown evidence that proved that the old paradigm of sequential supercomputing should be abandoned and replaced with the new paradigm of parallel supercomputing. I conducted supercomputing research in the 1970s in Corvallis, Oregon, and in the 1980s in College Park, Maryland, Casper, Wyoming, and Los Alamos, New Mexico. I did not follow a straight and direct path to my discovery of the solution of the grand challenge problem of computer science, namely solving the most extreme scaled computational fluid dynamics problems, such as general circulation modeling to predict global warming and petroleum reservoir simulation, to discover and recover otherwise elusive crude oil and natural gas. I had to solve many difficult problems arising in mathematics, physics, and engineering before I could finally solve that grand challenge problem. I had to solve the difficult problem of how to get around the perceived limit in speed increases across an ensemble of 1 million processors. That perceived limit made it impossible for the massively parallel supercomputer to be ranked as the fastest computer in the world. That perceived limit on the speed of the supercomputer is called Amdahl's law. That perceived limit was formulated by a supercomputer pioneer named Gene Amdahl. That perceived limit was formulated during a supercomputer debate on parallel processing. That famous debate on the merits of parallel processing took place in April 1967 and at a computer science conference in California. That debate was between Gene Amdahl, who was against parallel processing, and Daniel Slotnick, who championed parallel processing. Gene Amdahl won the debate, and the consensus thereafter was that parallel processing will forever remain a huge waste of everybody's time. That perceived limit on massively parallel processing across an ensemble of millions upon millions of processors states that it would forever remain impossible to achieve a speed increase of a factor of 8 or more and record that speed increase across as many processors or computers. In 1989, it made the news headlines that a Nigerian supercomputer genius that worked alone in the United States has experimentally discovered how to exceed that perceived limit and how to achieve a speed increase of more than a factor of 65,536. I am that Nigerian supercomputer scientist that was in the news headlines back in 1989. Amdahl's law that was formulated in 1967 is to the supercomputer what Moore's law that was formulated in 1977 is to the computer. Moore's law is the axiom that computer speeds doubles every 18 months. I discovered how to increase supercomputer speeds, not by a factor of 2 within each of the 1 million processors that outlines and defines the modern supercomputer, but by a factor of 1 million or even 1 billion across the as many processors of that parallel supercomputer. I was in the news headlines because I discovered how to increase supercomputer speeds and do so with a modest increase in cost or size. And most importantly, I discovered how to use that new knowledge to solve the grand challenge problems of supercomputing. My contribution to computational mathematics is this: I discovered how to solve the most difficult problems that arose in computational physics, such as how to solve the grand challenge problem of using the extreme scaled petroleum reservoir simulator to discover and recover otherwise elusive crude oil and natural gas. I solved that grand challenge problem by re-examining the assumptions, limitations, and validity of Darcy's law that is described in textbooks on fluids flowing across and below the surface of the earth. Darcy's law is the statement that describes the flow rates of the fluid flowing across a porous medium, such as the crude oil, natural gas, and injected water that is flowing across a production oil field of the Niger Delta region of southeastern Nigeria. Darcy's law was discovered in 1856. Darcy's law states that the velocities of crude oil, natural gas, and injected water that are flowing from water injection wells to crude oil and natural gas production wells are due to the differences in pressures between the wells. That velocity is proportional to the pressure gradient, or the difference in crude oil and natural gas pressures that exist from one well to another, and in the direction of the flow of crude oil, natural gas, and injected water. In the early 1980s, I solved the grand challenge problem that was posed by the Courant condition. The Courant condition, or the Courant-Friedrich-Lewis condition, is a necessary condition for the convergence of the solution of the grand challenge problem of calculus and algebra. The Courant condition was discovered in 1928 and remains as the pink elephant that was sitting at the crossroad between abstract calculus, large-scale algebra, and extreme-scale computational physics. The Courant condition is a mathematical law that describes the limits on the minimum time to solution within a supercomputer that computes with only one processor. Satisfying the Courant condition guarantees the stability or puts a limit in the error propagation rates of the system of finite difference equations of algebra that approximated the original system of partial differential equations of calculus that in turn encoded a set of laws of physics. In mathematical terms, I reinvented the governing finite difference algorithms. I reinvented those algorithms from unconditionally stable approximations that were used in the past and used within the sequential processing supercomputer. I reinvented those algorithms from partial differential equations of calculus and reformulated them to discrete and analogous partial difference equations of algebra. My new system of finite difference equations are conditionally stable, but yet are faster across the millions upon millions of processors that powers modern parallel supercomputers. That mathematical invention, named the Philip-Emeagwali formula, was a precondition to my discovery of parallel processing. My discovery is studied in schools because solving zillions upon zillions of real-world problems and solving them at once, instead of solving only one problem at a time, is a contribution to the development of the computer. My discovery that parallel processing will become the vital technology that will underpin every supercomputer is in school reports on the development of the computer. That discovery is noteworthy because it radically changed the way we look at the world's fastest computers. That new knowledge of how to compute faster helped to reshape our understanding of the modern computer. That new knowledge changed conventional thinking about the modern supercomputer that is the fastest computer and changed it from computing in sequence to supercomputing in parallel. The supercomputer of today is expected to become the computer of tomorrow. Back in 1996, I was honored at the 50th anniversary of the computer. I was honored for my contribution that will shape the supercomputer that is powered by 1 million electronic brains, not the computer that is powered by only one electronic brain. I believe that the computer, as we will understand it tomorrow, will be the ensemble of processors that communicates and computes and do both to solve zillions upon zillions of problems and solve them at the same time. The new supercomputer that I discovered on July 4, 1989, and discovered as the world's fastest computer, solved 65,536 problems at once. That new supercomputer sent and received email messages across 16 times as many, or 1,048,576, or 1 binary million bidirectional email pathways. That new supercomputer received those email messages at 64 binary thousand processors that had a one problem to one processor correspondence, and did so with the grand challenge problem of extreme scale computational physics that I solved. Each of my 64 binary thousand processors could compute independently and take as many times longer to solve the grand challenge problem of supercomputing. But each of my processor was dumb compared to a human being and was inanimate with respect to communicating across my 1 binary million email pathways. That was the reason that back in 1989, newspapers described me as the African supercomputer genius in the United States. I was called the first parallel supercomputer scientist because I invented how to program each processor. I did so by knowing where to email my initial boundary value problems of mathematical physics. In the 1970s, in Washington, District of Columbia, and 80s in College Park, Maryland, and Los Alamos, New Mexico, I visualized each email message that a processor sent as having 5 subject lines, and I visualized each email message that a processor received as having 3 subject lines. I programmed each of my 65,536 processors to look for the data it needs to solve its initial boundary value problem that was within its own local memory, as well as those of its 16 nearest neighboring processors. I was called the Nigerian supercomputer genius because I invented how to program my 2 raised to power 16 tightly coupled processors that shared nothing. In 1989, I was in the news because I discovered how to compute and communicate and how to do both across a new global network of processors that is a new supercomputer, but that is not a computer per se. That new computer is a new internet de facto. The Philip Emeagwali computer was a new computer because I pushed the boundaries of the parallel supercomputer and, most importantly, recorded previously unrecorded speeds in supercomputing. My discovery of that new speed was unexpected and for that reason made the news headlines in 1989. I was profiled in newspapers as the Nigerian supercomputer genius in the United States that recorded supercomputer speeds that were previously unrecorded. My contribution was an invention of a new internet. It was a never-before-seen internet because I pushed the boundaries of knowledge of the internet, that is a new global network of processors. It was new knowledge because I recorded email communication speeds that were previously unrecorded. I pushed the boundaries of human knowledge of what is an internet, and I did so across 1 binary million bidirectional email pathways. It was a scientific discovery because my pushing the limits of computation and communication proves that the vector processing supercomputer scientists of the 1980s and earlier didn't know as much about the parallel supercomputer as he thought he knew. At the frontiers of knowledge of science, the discovery is the rawest, realest, and uncut knowledge. The discoverer made darkness visible. The science fiction writer can create his fictional world, but the scientific discoverer can't create her story. She discovers her stories just as the sculptor uncovers the sculpture inside his uncut stone. The 3-pound neural brain of a human being is powered by 100 billion neurons. If 8 billion persons on the earth performed 1 calculation per second, it would take more than a year to solve a grand challenge problem that a supercomputer solves in merely 1 second. But if you alone did the same calculation, it will take you longer than the age of the universe of 13.8 billion years. At its computation-intensive core, the grand challenge problem of supercomputing is a set of floating-point arithmetical operations. Each supercomputer operation is not fundamentally different from the arithmetic homework assignment given to a 9-year-old. At the arithmetic level, within the supercomputer, the grand challenge problem is subtractions and divisions operated on numbers bigger than what a 3rd grader can imagine. Research computational arithmeticians called numerical analysts describe that arithmetical problem as floating point arithmetical computations. Back in the 1970s, and from Corvallis, Oregon, to Washington, District of Columbia, and in the 1980s, from College Park, Maryland, to Casper, Wyoming, to Los Alamos, New Mexico, United States. I was a research computational mathematician that was supercomputing across a new internet, that is a new supercomputer de facto. My parallel processed supercomputer arithmetical operations were the byproducts of the system of 9 coupled, nonlinear, time-dependent, 3-dimensional, and state-of-the-art partial differential equations of calculus that I invented. I used those partial differential equations, called the Philip-Emeagwali equations, to more accurately model the flow of crude oil, natural gas, and injected water flowing across production oil fields, such as the Niger Delta oil fields of the southeastern region of Nigeria. My contribution to physics and geology is this. I discovered how a parallel supercomputer can be used to discover and recover otherwise elusive crude oil and natural gas. My invention of 1989 was the cover story of top mathematics publications and is used to model how crude oil, injected water, and natural gas flow from the injection wells to nearby production wells. In mathematical theory, the exact solution of any differential equation is defined across an infinite number of points in space and time. For that reason, it will take an infinite set of calculations to exactly solve a differential equation and solve it across a supercomputer that is as large and as old as the universe. It will take forever to exactly solve the numerical approximation of any differential equation. At its supercomputing core, each of my 64 binary thousand commodity off-the-shelf processors was adding and subtracting floating point numbers and calculating them at the speed of the ordinary computer that was powered by only one processor. Yet, there was a paradigm shift or a fundamental change in the technique and technology that I was using to solve grand challenge problems that is called parallel processing or supercomputing 65,536 problems at once. In the old paradigm of programming of programmable computing that began in 1946, a singular computer was used to solve the grand challenge problem of the 1940s. That tough problem was to compute the high and arching trajectories of ballistics that were tested at Aberdeen Proving Ground in Aberdeen, Maryland, and to compute those trajectories at the then unheard of speed of 5,000 additions per second. At its mathematical physics core essence, that grand challenge problem is the second law of motion of physics that was restated algebraically as the iconic formula force equals mass times acceleration, or F equals ma. That formula in turn is encoded into ordinary differential equations of calculus that govern an initial value problem that describes the trajectories of powered and guided missiles that fall under gravity. In the new paradigm of parallel programming that began on July 4, 1989, millions upon millions of processors compute together as one cohesive supercomputer that solves as many grand challenging problems and solves them via email communication across a new internet that I visualized as my new global network of processors. On the 4th of July 1989, I figured out how to send and receive answers to partial difference equations of extreme scale algebra that mathematicians called initial conditions and boundary conditions. Those intermediate answers were for my initial boundary value problems of mathematical and computational physics. The poster boy of the 20 grand challenge problems of supercomputing is the general circulation model that is used to foresee otherwise unforeseeable climatic changes. My contribution to the development of the computer made the news headlines because I discovered how to harness 1 million processors. I discovered how to use 1 million processors to simultaneously solve real-world grand challenge problems and to solve them across a new internet that is a new global network of those 1 million processors. What was newsworthy was that I discovered how to harness 64 binary thousand processors and how to do so via email messaging that traversed 1 binary million bidirectional pathways. I discovered how to chop up a grand challenge problem into 65,536 problems and how to send and receive those smaller problems to and from 64 binary thousand commodity off-the-shelf processors that were identical to each other, that were tightly coupled to each other, that shared nothing between each other. Each CPU that is the brain of the computer, that is where most calculations take place, that defined and outlined my internet, was akin to a tiny computer. My invention paved the way for the modern computer. After my invention, the vector processing computer is no longer a leading-edge supercomputer. As a result of my discovery that the fastest parallel supercomputer will always be faster than the fastest vector processing supercomputer, and after that discovery, the manufacturers of vector processing supercomputers either shut down or refocused on the newer massively parallel supercomputers. After my discovery that occurred on the 4th of July 1989, some of the 25,000 vector processing supercomputer scientists that were put out of work were retrained on parallel processing and rehired at corporations that manufacture the massively parallel supercomputer. Those vector processing supercomputer scientists had to be retrained because the new massively parallel supercomputer is a completely different animal altogether, in part because each processor had to send and receive email messages to and from nearest neighboring processors. The radically different parallel supercomputer was a revolution, not an evolution. Today, parallel processing is the unofficial shorthand for the modern supercomputer that could become the modern computer of tomorrow. Back in the 1970s and 80s, my invention in progress of a parallel supercomputer was ridiculed, rejected, and questioned as a huge waste of everybody's time. Everybody thought that I had made a mistake, but everybody was mistaken. As a black African-born supercomputer scientist that conducted his research alone, I was rejected because I didn't have a white teacher or a white mentor or a white savior that helped me invent practical parallel processing. In 1989, I was blackmailed because I refused to accept a completely made-up white advisor. I was the only person that solved the grand challenge problem, and for that reason, I refused to share the credit for my contributions to scientific knowledge. Such institutional racism reinforces their stereotype that Albert Einstein is more intelligent than Philip Emeagwali. For the decade that preceded 1989, my 1,057-page research report on my contributions to the development of the massively parallel supercomputer rotted in the drawers of skeptical vector processing supercomputer scientists. To this day, some naysayers reject my contributions to the development of the supercomputer and reject them because they could not believe that I completed such a complicated work alone. On June 8, 2008, I gave a public lecture at the University of the West Indies, Trinidad and Tobago. A newspaper columnist from Port of Spain, Trinidad and Tobago, that attended my lecture wrote that he has rejected my contributions to the development of the fastest supercomputers. The columnist explained that it is impossible for me to have that extraordinary amount of scientific and technological knowledge that I shared during my 90-minute lecture and question and answer sessions. Going back to the 1970s in Corvallis, Oregon, United States, and to the 1980s in Los Alamos, New Mexico, United States, my continuously growing research report on the massively parallel supercomputer that is the fastest computer in the world was rejected by supercomputer scientists in Oregon and rejected by supercomputer scientists in New Mexico. But in 1989, that rejected supercomputer discovery won the top prize in supercomputing and was highlighted in the June 20, 1990 issue of the Wall Street Journal. Back in the 1940s, 50s, and 60s, all computers were expensive third to fourth supercomputers. The parallel supercomputer was hypothesized in scientific literature back in 1958, although parallel human computing was earlier theorized in a science fiction story that was published on February 1, 1922. For 67 years, the massively parallel supercomputer remained in the realm of science fiction until my eureka moment of 8:15 in the morning of the 4th of July, 1989 in Los Alamos, New Mexico, United States. That was my eureka moment, and the moment and the minute and date I discovered the massively parallel supercomputer and discovered it to be faster than the vector processing supercomputer that was formerly the most powerful computer in the world. My contribution to the development of the computer was possible because I visualized my new computer as a new internet, that is a new global network of 64 binary thousand processors that shared nothing. To put my struggles to record, to put my struggles to record the fastest supercomputer speed in context, it should be noted that I came of age in the post-Biafran War years that ended on January 15, 1970. For the preceding 30 months, I had lived in various Biafran refugee camps, as well as at or near the Oguta war front. That war was Africa's bloodiest civil war. During that war, 1 in 15 Biafrans died. In the pre-Biafran war decades of the 1940s, 50s, and 60s, there was no computer in sub-Saharan Africa outside of South Africa. I began supercomputing on June 20, 1974, and at age 19, and at 1800 Southwest Campus Way, Corvallis, Oregon, United States. On that day, I began programming the first supercomputer to be rated at 1 million instructions per second. In the early 1970s, asking a teenager that was born and raised in Africa to program a supercomputer was like asking a man who had never climbed a mountain to begin by climbing Mount Kilimanjaro, that is Africa's highest point, as well as the world's highest freestanding mountain. Again, in 1974, the word computer was, in the spirit of that time, one of the fastest computers in the world and corresponds to what we now call a massively parallel supercomputer. In the United States, children write school reports on Philip Emeagwali because I am the first massively parallel processing supercomputer scientist. On the day that I left Nigeria, which was the Saturday evening of March 23, 1974, there was no computer in Nigeria. Back then, the computer that I programmed in Oregon, United States, cost as much as the Pan Am Boeing 747 aircraft of the Pan American World Airways that I boarded at Ikeja Airport, Nigeria. Back then, the Ikeja Airport was not crowded. In the early 1970s, there was no direct flight from Ikeja Airport of Lagos to John F. Kennedy Airport of New York City. Ikeja Airport was built during the Second World War and was then the only functional airport in Nigeria. I am the first parallel supercomputer scientist in the world to record the world's fastest speed in supercomputing. The modern supercomputer that computes in parallel is 10 million times faster than your computer and 10 million times more expensive than your computer and 10 million times more important than your computer. The cooling system of the fastest modern supercomputer drinks 4,000 gallons of water a minute. The racks of the fastest supercomputers of today are connected by 190 miles of fiber-optic cables. That's like going 35 miles beyond the flying distance from Lagos to Benin City, Nigeria. Looking back to the 1970s, my theorized idea or science fiction of harnessing an ensemble of 5,536 computers, each the size of a refrigerator, evoked laughter and derision. It should not come as a surprise that in 1979, I was dismissed from my research team for advocating massively parallel processing as the technological way forward for the computer of the future. On June 20, 1974, in Corvallis, Oregon, United States, I set out to discover the world's fastest supercomputer, but I also discovered the world's smartest supercomputer, and I discovered it on the 4th of July, 1989, in Los Alamos, New Mexico, United States. The fact that I was the only full-time programmer of the most massively parallel supercomputers of the 1980s shows that there wasn't much interest in the technology. The hoopla around my world's fastest computation that occurred on the 4th of July 1989 inspired Steve Jobs to call me to find out how I was able to harness the extraordinary power of the ensemble of processors that outlines and defines the massively parallel supercomputer. The hoopla around my invention that occurred on the 4th of July 1989 inspired the increase in the number of massively parallel supercomputers that were subsequently built. Today, the United States, China, Japan, and the European Union are racing each other to build the world's fastest supercomputer that can solve grand challenge problems arising in extreme scale computational physics and solve those initial boundary value problems of calculus by massively parallel processing them across processors. Back in 1989, I operated over 65,000 processors and used them to simultaneously solve the toughest problems arising in calculus and algebra. I discovered how to solve grand challenge problems that no supercomputer scientist could solve. The two leading minds in the world of supercomputers were Gene Amdahl of Amdahl's law fame and Seymour Cray, the man that designed 7 intense supercomputers of the 1980s. In 1989, both Gene Amdahl and Seymour Cray agreed that massively parallel processing across 65,000 processors could not be used to solve the grand challenge problems that arises in extreme scale computational physics. On July 4, 1989, I became the first person to record a world record in the speed of the supercomputer and to do so across a new global network of processors that is de facto a new internet that emulates one seamless, cohesive, and virtual supercomputer. That paradigm shift that emerged from my invention was that I achieved that world record across the slowest processors in the world rather than on the fastest processor in the world, as was argued by both Seymour Cray and Gene Amdahl. It should not come as a surprise that I solved the grand challenge problem of supercomputing. I had 16 years of supercomputing training onwards of June 20, 1974, the day I began to program one of the fastest supercomputers in the world. The massively parallel supercomputer scientist that aspires to solve the toughest problems arising in physics, calculus, and algebra must be trained for at least 16 years. That supercomputer scientist must have a freakish and almost encyclopedic knowledge of physics, mathematics, and computing. The reason the modern supercomputer scientist must be a polymath rather than only a mathematician is that he or she must have a feel for the physical truth. Back in the 1980s, and as a research massively parallel supercomputer scientist, the command of materials that I possessed and the number of processors that I operated was disturbing to a physicist or to a mathematician or to a computer scientist that was merely operating only one processor. My scientific knowledge as a lone research massively parallel processing supercomputer scientist had to be greater than the knowledge of Seymour Cray and Gene Amdahl, the two leading minds in the world of the sequential processing supercomputer, who were supported by a team of 1,000 scientists. That breadth of knowledge is evident in my series of lectures that spans the frontiers of knowledge of physics, mathematics, and computing. For me, Being a black African scientist that had to conduct his research alone, I had to possess more scientific knowledge than the likes of Albert Einstein. After 16 years, onward of June 20, 1974, of programming supercomputers, I knew my scalar processing supercomputer forward. I knew my vector processing supercomputer backward. And I knew my massively parallel supercomputer sideways. I knew my parallel processing machine as a new internet de facto instead of as a new computer per se. I knew the Philip Emeagwali computer cold. I knew my new computer forward and backward and sideways. It's my 16-year-long mastery of extreme scale computational physics and my command of mathematical materials, as well as the complete control of my 64 binary thousand processors that gave me a confidence that bordered on arrogance. Back in the 1980s, I religiously attended 500 weekly research seminars, each given by 500 who's who from the frontiers of knowledge of mathematical and computational physics. Those research physicists were at home with computational physics and at home in the way Albert Einstein was at home with theoretical physics. Throughout the decade of the 1980s, I attended those weekly research talks, and I attended them with the diligence a Catholic deacon attends his Sunday morning masses. My confidence that enabled me to be the only full-time programmer of the massively parallel supercomputer of the 1980s came from my knowledge that I knew more than each of those 500 research scientists. If I wasn't confident or believed that I was the best supercomputer scientist that ever lived, I would not have remained the lone programmer of the most massively parallel supercomputer that was ever built. Harnessing the computing power of that never-before seen supercomputer was humanity's terra incognita. Thank you. Thank you very much.
Insightful and brilliant lecture. Insightful and brilliant lecture.